Hello and welcome back to another lesson on Learn with Rymer. My name is Rymer. To fellow students who may be returning, obviously you know me as Riley. Today we're going to go on part 2 talking about parallel circuits in a 3-part series looking at series circuits, series parallel circuits, and how to solve those equations with given information with our Ohm's law and our Kirchoffs laws within electrical troubleshooting. We're going to break down the different rules that apply to our parallel circuits. And then on my other side, we're going to look at 2 different types of circuits. This one's going to have 3 branches that have individual resistors, each with their own resistance value. After this one has been solved, we're going to break down a second parallel type circuit that's going to include multiple resistors across each leg and what that looks like with regards to our total resistance throughout the entire circuit. So the first thing we need to discuss with regards to our parallel circuits, rule number 1, voltage applied to all paths is going to be equal. I like to state this in a way that says voltage is constant throughout a circuit. So let's apply that to our circuit here. If I have a battery set that has 12 volts applied to it, that 12 volts is going to be applied equally to each of these parallel legs. That's what that means. So that voltage is applied to all paths. It's going to be equal. My second rule, current through each path is going to be determined by the resistance on that path. In my schematic here, I have 3 different legs. The amount of amperage that's going to be drawn on each of those legs, allowed to flow on each of those legs, if you will, is going to be determined by the resistance value on that given branch. Rule number 3, we have to add the resistance in a parallel circuit, and that's going to see the total resistance go down. So what I like to say, if you think about at a grocery store, if there's 2 lanes that are open and I have a long lineup, one single line waiting to filter into those 2 lineups. If a third cashier opens up, I've now created another path for those customers to come through with their groceries, and then that will overall reduce the amount of resistance within those 3 lanes. So my overall total resistance goes down with the addition of a third branch. Fourth rule, removing a path will see the total resistance go up. If I remove those extra paths, my overall resistance goes up. When we're adding circuits without really considering the existing amperage loading, that's why we'll see these blown fuses within our circuitry. Fifth rule, the total resistance always will be less than the resistance of any individual path. So looking at this circuit with a single resistor in each path, I can assume that my total resistance is going to be less than 3. Rule number 6, total current is equal to the sum of all paths. So I add all my amperages for total amperage. My final rule, the parallel circuit has more than one path. I think in the name that's kind of a given. We're going to apply these rules to this equation. We're going to figure out how much amps we're drawing across each branch, and we're going to figure out the amount of volts that are going to be used at each resistor. And now in this one, it's going to be relatively easy, because if we think back to our series circuits, all voltage in a circuit will be consumed through all the resistors. If I have voltage applied equally to all paths, I think it's safe to say that that single resistor, barring no unwanted high electrical resistance, will be used at that one resistor. I will see all 12 volts drop at each of these resistors on this path. But what's going to change is the amount of current that I'm drawing on each pathway. In order to figure that out, knowing I have 12 volts, and I have a resistance value, 1 ohm, I'm going to divide that 1 into the 12. That's going to give me an amperage value of 12 amps. Just using this tradesman's triangle, I divide across the top and I always multiply across the bottom. Ammeter hooked up in series is going to read 12 amps. We're going to do that same math for each of these branches now. 3 ohms, I have 12 volts. My ohms changes to 3 ohms. That's going to give me a 4 amp draw across that leg. We do the same thing on that top branch. If I have a 4 ohm resistor, 12 divided by 4 is going to give me a 3 amp draw. Now I have all of my amperage draws across the individual resistance paths. we can figure out how many amps are flowing from this parallel circuit. I'm going to do a quick sum, total amperage. As per my rules, the total current is equal to the sum of all of the paths. So we're going to take the amperage draw at each path, 12 plus 4 plus 3 should give us 19 amps. I will have 19 amps flowing from that battery set. Using this information, I can further extrapolate how much total resistance I'm going to have. So my total resistance, now that I have a total amperage draw, 19 amps and 12 volts, will give me a total of 0.63 amps. To further determine if I've done my math correctly, my total resistance will always be less than the resistance of any individual path. Let's double check and see if that is true. Is my 0.63 amps smaller than my 3 ohms resistance on my single leg? Yes, that is true. Has all my voltage been consumed at each of my branches? Yes, that is true. That is all I need to do to solve this type of parallel equation. Now, if you're finding this helpful, you know what to do. If I can achieve my goal of helping one extra person beyond my scope of my classroom, then I've done my job. Let's take a look and clean this off and get a different type of parallel equation drawn up on this board. So I've changed over my structure. I've added a couple of additional resistors. What I've done, I've added an 8 ohm resistor and a 6 ohm resistor in place of my earlier, I don't remember the value, and 2 ohm resistors in place of, I don't remember the value of that resistor on their last equation. Doesn't matter. I'm still going to use a 12 volt voltage source or 12 volt battery source. Let's dive into how to solve for this equation. The process doesn't change. All my rules for my parallel circuit are still down here. That all applies in this same parallel circuit. The only difference is how we address these two paths with the 2 resistors on them. First thing we're going to do, we apply the 12 volts to each branch equally, because voltage is constant in a parallel circuit. Knowing that 12 volts is available at each branch, the difference with this one where we have 2 resistors is we need to know how many amps are flowing through here so we can determine how many of this available voltage is going to each resistor and being consumed or used up. In order to do that, we're just going to add the 2 resistance values. That's going to give me, on the case of this bottom branch, 4 ohms resistance, and I'm going to apply that 4 ohms to that 12 volts. That's going to give me my amperage draw. If I have 12 volts and I have 4 ohms, that's going to give me a 3 amp draw. Okay, so I have 3 amps flowing through that leg of the circuit. I then take that 3 amps that's available, I apply it to each of my resistors. That's going to give me a total of 6 volts consumed at each resistor because they're the same. They're going to use the same voltage. This middle branch is unchanged from our last equation. We're going to take that 12 volts, apply it to the single resistor because all 12 volts are going to be consumed. That's going to give us a 4 amp draw across that leg. Moving up to our top branch, the process is the same, but now we have 2 different resistance values. We add those 2 values. That's going to give me a 14 ohms total. Let me erase this stuff. 14 ohms, and we're going to put that into our 12 volts available. 0.86 amps is being pulled through this branch. Now that I have that amperage draw, that amps is going to flow through each of those resistors. I'm going to take this 0.86 amps and I'm going to multiply it by each resistor to see how much of the voltage each of those resistors consumes. First, we'll do 0.86 times 6, 5.16 volts being used up at that first resistor. And we will apply that 0.86 to an 8 ohm resistor, 6.88 volts. Now, barring any rounding errors, I rounded up to the nearest second decimal place. The sum of those two should equal 12 volts, which they do, barring my rounding. All 12 volts are being consumed at each branch. We have 2 more steps to do to complete this equation. We're going to come up with the sum of all of our amperages. 4 plus 3 plus 0.86 will give us 7.86 amps, leaving that battery and returning to that battery. The final step is to figure out our total resistance. Our total resistance in this instance looks a little different. It should be smaller than any individual branch's total resistance. While I have two 2-ohm resistors in this lower branch, the sum is 4. My resistance for the circuit should still be less than this 3 ohms, the smallest branch worth of resistance. So if we take our 12 and divide 7.86 into it, will give us 1.53. Is my total resistance lower than my lowest leg's resistance value? Yes, it is. It is less than my 3 ohms. Again, if you find this helpful, you know what to do. Stay tuned for more. The last one that I need to approach is our series parallel. I take a little bit of a different approach, but we'll get to that in the next video. Thanks, and have a great afternoon.